This begins the first of several lectures on model selection. And the specific approach to model selection that we'll look at is known as Bayes factor. We'll start by looking at the model selection problem through the lens of Bayes' rule. And here's how we formulate the basic problem. We're given an indexed set of models, M1 through m, and these could be different regression models, for instance. They could be different formulations for the regression. For example, a strictly main effects model, a main effects with interactions, a polynomial model. There could be lots of different models that we're considering using for our particular problem. And we assume we've got priors for each of the models, which we'll designate by P of mi, I again indexing the model. And then the posterior distribution for the model, for the choice of model, is given by Bayes' rule. So it's going to be the ratio of the data, and we'll let script D represent the data, given the particular model, times the prior probability for the model, and then over the probability of the data itself. And again, these can be probability mass functions or probability density functions. The unconditional likelihood of the data, the denominator here, then we can express, as we've done over and over again, using conditioning or the sum rule. Model MI is parameterized by some parameter set, let's say, and we'll call that theta I. And the model likelihood then can be expressed again by conditioning, and we'll show this through integration because mostly these parameters are real valued. And so we just look at the conditional distribution for the data, now conditioned on the model parameters as well as the model itself, and then times the density function for the parameters given the model choice, and then of course integrated over all values of theta, all values of the parameter. And this could be a vector of parameters. In discrete parameter space, of course, the integral is replaced with a summation. So if we do have discrete parameters, then we can of course replace that integral. I note that the number of parameters dimension of theta I doesn't have to be the same for every model. So in other words, there are models, an example would be a model that is a main effects model versus an interaction model. We have additional parameters in the interaction model. So the way Bayes factor works is that we compare two competing models, say MI and MJ, and we can do that just looking at the likelihood ratio, in fact, the ratio of the posteriors. And the ratio of the posteriors is just expressed as the ratio of the likelihood or probability, if it's a discrete case, which typically it is for models, of the model I given the data over the probability of model J given the data. And we can look at this again with just carrying through Bayes' rule, and notice that the denominator in Bayes' rule cancels, since that's just the likelihood of the data itself. That cancels, and we're left with the likelihood ratio and the ratio of priors. And the likelihood ratio is what we call Bayes factor. This is the ratio of the likelihood of the data given each choice of the model. And this doesn't require any integration or summation over the models. It just requires computing that likelihood ratio and the ratio of the priors, and that's all we need to do. We have one noted caveat that this likelihood for the model, or the probability of the model, only refers to the probability relative to the set of models specified. So this isn't the absolute probability that the model fits well. It's just over the set. So this is over our set of models that we're considering. If we've left something out, then that won't be considered here, and it won't be part of the Bayes factor calculation. So the ideal here is you want to consider all possible models that are likely to be useful for your particular data for Bayes factor to work. These are the normal rules of thumb regarding the values of Bayes factor. Typically, if you get a value between 1 and 3, you consider the strength of evidence for any one model to be anecdotal. So if a model shows a strength, a Bayes factor of about let's say 1.5 or 2, it's only anecdotally better than another model. Between 3 and 10, we consider it to have moderate strength. 10 to 30 is a strong evidence of that model being the correct one. 30 to 100 is very strong, and greater than 100 we consider it to be extreme. It's an extremely strong case for that model being the right one. So let's take a look at an example of this and consider just a simple case of flipping coins. So we've got two possible models here. First model is that the coin is fair. The second model is that the coin is biased. So we're going to take a coin and we're going to flip it. And the question is it fair or biased? And those are the two model choices that we have. Notice that we need a domain for our theta, which is the probability of a flip coming up heads. And we'll just discretize this domain. So we'll say it goes between 0.1 and 0.9. Any one of those probabilities in that range. Again, indexed by, a spacing of 0.1. Now, as we saw, in order to calculate the likelihood, we're going to need to find the distribution for the probability of each of these values for theta, given the type of coin we have, the model, whether it's fair or biased. So we're going to need to calculate the probability of theta, each one of the values for theta, given the model being either fair or biased. So in the diagram on the left, A, we see the case of the values for theta given a fair coin. And this is, you can consider this to be the prior for theta, but it's basically the distribution that we're going to use inside that sum rule in order to calculate the likelihood for the data given the model. So in the case of A, which is the case of what's the value, what do we think the probability is that theta will take on any one of the values 0.1 to 0.9, given that we have a fair coin, this is saying that we think it's very likely that if it's a fair coin, theta will have the value of 0.5. In fact, we think it's just under 0.8 that it'll have that value. We think that it has some likelihood around 0.1 of being 0.4 or 0.6, very little likelihood of being 0.3 or 0.7, even less likelihood of being 0.2 or 0.8. Whereas in the case of the values for theta given a biased model, then we see that the likelihood, the probability for it being 0.2, 0.3, 0.7, or 0.8, they're all equal, and they're somewhere around 0.17. So this is the probability that we think that the theta takes on one of those values, given that we have a biased coin. We think it's a little bit less likely, but still probable that it could take on the values 0.4, 0.6. Has almost no likelihood that it'll have the value 0.5 because that'd be a fair coin. And then there's some likelihood of it being 0.1 or 0.9. So that's the distribution for theta given the model of a biased coin. That's shown in B. And of course, as we said, the model of theta, or the probabilities for the different values for theta given the model of a fair coin, is shown in A. With those probabilities, then, we can now find the likelihood for each model. And again, the likelihood is given by the sum rule. And since we've discretized the thetas, we're going to do this literally with a summation, summing over all the values for theta between 0.1 and 0.9. And all we're doing now is we're replacing that likelihood function of the data given theta in the model with the actual value of the likelihood, which is theta to the number of heads and 1 minus theta to the number of tails. And then that, of course, times this distribution that we just derived for theta given each choice for the model. So we next just plug in the values here. So we start with 0.1, that's to the number of heads we have, 1 minus 0.1 of the number of tails. The probability that theta is equal to 0.1 given the particular model, and we found that on the previous slide. And we just do that all the way up to 0.9, and we get the likelihood for the data given each of the models. And we can take that and compute Bayes' factor then. So let's assume that the likelihood is, or the priors for each of these two is equal. So the likelihood, the prior distribution for a fair coin is equal to the prior distribution for a biased coin. So they cancel out then, and we're left just with Bayes' factor, the likelihood ratio of the data given a fair coin over the likelihood ratio of the data given a biased coin. And let's consider an example here of actually throwing a coin and see what we get. So suppose we flip a coin and we get 5 heads and 2 tails. And then we can compute then the likelihood, and it turns out to be 0.007 or about 0.008. And in the case of a biased coin, it turns out to be 0.007. So the Bayes factor then is not much more than 1. So we have little evidence to suggest we have either a fair or biased coin. So we have no strong evidence for either model. However, if we were to continue flipping the coins and ended up with 50 heads and 20 tails, then things would change a little bit. The likelihood of this particular set of data, 50 heads and 20 tails, is 1.5 times 10 to the minus 20, and with a fair coin. And with a biased coin, it's 1.4 times 10 to the minus 19th. And so Bayes' factor then turns out to be 0.1, which indicates that we have around 10 times the belief of a biased coin than we do for a fair coin. So this is giving us much stronger evidence that we have a biased coin. And this is how Bayes' factor is used to choose between models. It gives us a sense of how strong the evidence is for one model versus another.